Woohoo! Time for some calculations. So, first problem, we want to find the entropy change when we heat 3 kilograms of water from 20 degrees Celsius to 50 degrees Celsius. So our equation, S stands for entropy. I don't think I mentioned that in the other video, but hopefully you figured it out. Our equation for change in entropy is Q over T. In this case, if we're heating up some water, to find Q, we're going to do MC delta T over T. Well, since T is changing and we have to divide by temperature, technically what we should do is take an integral, but we'll get close by doing the average temperature over this temperature change. Okay, so now we just got to plug in some numbers. We've got the mass, 3 kilograms. We want the specific heat of water, and I want my entropy to come out in joules per Kelvin, so we're going to use the specific heat in joules per kilogram degrees Celsius, and that was 4,186. The change in temperature from 20 to 50 is a 30-degree increase, so we got positive 30 there. We do have to be careful on our signs because entropy can decrease in part of the system, and so we would have a negative sign on our delta T if that were happening. And then the average temperature, as this water is heated from 20 to 50, and we're going to assume it was heated at a uniform rate, so that's just the midpoint there, which is going to be 35. We do need our temperatures in kelvins, not our delta T's, because those are the same in kelvins and Celsius. So we got to add 273 here. And then that's it. There's our calculation. Not too tricky, and this works out to be 1223 joules per Kelvin of entropy added to our universe by heating up some water. Alright, next, if we have a shot put 2 kilograms and we're dropping it to the ground from 1.5 meters, what is the change in entropy, assuming that the ball is at 293 kelvins? Well, you might say, well, I don't know anything about Q in this case. We've got some height here, so we've probably got some potential energy. Well, since Q is just the heat that flows, all of the energy that you start with becomes heat, so that's the amount of heat that flows. So to find Q over T, the Q is the kinetic energy right before it hits the ground. Divide that guy by T, and we could calculate that, but we already know that this kinetic energy equals the gravitational energy it started with, so we can just go with this expression here and get the change in entropy. If you remember, gravitational energy is mgy over T. We're given all of these numbers, so 2 times 9.8 times 1.5, and then in this case the temperature is not changing. We're assuming it's pretty constant here, so we just divide by that number. We don't have to worry about averaging it. And again, throw that guy in your calculator and you get a much smaller change in entropy for dropping a shot put than you do for heating up 3 kilograms of water. Alright, one more example and then we'll be done. Here we've got water being mixed. So when you do that, some of the water, the cold water, gets heated up and the hot water gets cooled off. And we want to figure out the net change in entropy of the system. So we can treat the hot and cold water as two different parts of the system. So the total change in entropy of the system is the change in entropy of the hot water plus the change in entropy of the cold water. And so for each of these we can have Q over T, so Q of the hot over average temperature of the hot plus Q of the cold over average temperature of the cold. And if you're thinking, well, heat is flowing out of the hot water, so you might want to put a negative there. I'm going to wait until later. I'm going to put the negative in when I get the delta T. You can put it in either time, just don't put it in both times, one time or the other, and it will all work out fine. So for each of these, we're going to do like we did in the first example, where we have MC delta T of the hot over average temperature of the hot plus MC delta T of the cold over the average temperature of the cold. Coming back over here, if we factor out that MC, there's an ugly M, but then you're going to have delta T hot over average temperature hot plus change in temperature of the cold over the average temperature of the cold. Looks like my H went away. Alright, now we can start plugging in numbers and thinking about changes and averages and whatnot. M is 10 kilograms for both of them. Made it nice by having the same amounts. C is the same C we used previously, where we want joules per kilogram, so 4,186. Delta T for the hot. Well, if I have equal amounts of water, one at 40 and one at 60, the final temperature, sorry, one at 40 and one at 80, I'm getting a little ahead of myself. The final temperature is going to be 60 degrees. It's going to meet in the middle if you have equal amounts of the same substance. So to go from 80 down to 60 is a change of negative 20. And the average between 80 and 60 is 70. And again, we got to convert to kelvins here. So there is that term for the hot. Plus the change in temperature of the cold. That one goes from 40 to 60, so it was also a change of 20, but this time it's positive. The average of this is not 70. The average between 40 and 60 is going to be 50, and that really is going to make all the difference, because this negative here is going to give us a decrease in entropy, but it's divided by a larger number in the numerator, so this quotient here is going to be smaller than this one here, so the positive change in entropy is going to be greater than the negative change in entropy, and so the overall change will come out positive. So anyway, you can throw that fun thing in your calculator. Works out to be 151.1 joules per Kelvin. And if you ever get a negative here, that means you screwed something up if you're finding the change in entropy of the system. If you're solving for the change in entropy of one part, you could get a negative sign there, but overall always going to be positive. There's the second law at work. See you next time.